Hello guys, welcome back to our channel. Welcome to Reinforcement Learning, how AI masters the art of playing games. In today's video, we'll uncover the fascinating world of artificial intelligence and explore how machines learn to play and even dominate some of the most complex games ever created. From beating world champions in chess and Go to mastering video games like Atari and Dota 2, reinforcement learning has powered some of the most groundbreaking achievements in AI. But how exactly does an AI agent learn to play games? What motivates it? How does it improve over time? And what does this mean for the future of gaming, learning, and beyond? Stick with us as we dive deep into the concepts, algorithms, real-world applications, and exciting case studies behind reinforcement learning. So let's talk about what is reinforcement learning. Reinforcement learning, RL, is a branch of machine learning that focuses on training an agent to make decisions by interacting with an environment. The agent learns by receiving rewards or penalties for its actions, gradually improving its behavior to maximize the total reward over time. Key components of reinforcement learning. Agent, the learner or decision maker. It could be a robot, a computer program, or an AI model in a game. Environment, everything the agent interacts with. This can be a video game, a simulated world, or a real-life scenario. State, S, a snapshot or situation of the environment at a given time. For example, in chess, the current arrangement of the pieces on the board is the state. Action, A, the move or decision the agent makes. In a game, this could be move left or jump. Reward, R, a numeric score the agent receives after taking an action. Positive rewards encourage the behavior, while negative rewards discourage it. And policy, P, the strategy or rule that the agent uses to decide its actions based on the current state. A value function, V, a function that estimates how good a particular state is, considering future rewards. Q value, Q function, evaluates how good a state action pair is. It's used in Q learning to guide decision-making. Types of reinforcement learning. Model free RL. The agent learns directly from experience without understanding the environment's internal mechanics. Model-based RL. The agent tries to model the environment's dynamics and predict future outcomes to plan better actions. So now deeply understand why games are perfect for reinforcement learning. First one, well-defined rules and goals. Clear rules. The logic of how the environment behaves is well-structured and known. Defined objectives. Whether it's capturing a flag, winning a match, or achieving a high score, the goals are clear. Second one, quantifiable rewards. In games, rewards are numeric, for example, points, wins, losses. They're often immediate. For example, score goes up after a successful move. Third one, repeatability and simulation. Games can be played millions of times at high speed. Reset instantly after each game or action. Fourth one, safe and controlled environments. In the real world, learning through trial and error can be dangerous or costly. For example, training a self-driving car. In games, mistakes have no real-world consequences. Agents can experiment freely. Fifth one, varied and complex challenges. Games offer different genres, puzzle games, racing, strategy, shooting, etc. Levels of complexity, from simple 2D games, for example, Pong, to complex 3D strategy games, for example, StarCraft II. Sixth one, human benchmarks. Games are designed for human intelligence, competitive, for example, chess, Go, Dota 2. Seventh one, encourages strategic thinking and planning. Advanced games require multi-step planning, prediction of opponent behavior, adaptation to changing conditions. Examples of games used in RL training: Atari 2600 games, used by DeepMind to train agents using Deep Q networks, DQN. Chess and Go, mastered by AlphaZero and AlphaGo using deep reinforcement learning. StarCraft II, AlphaStar demonstrated strategic RL in a real-time, complex, partially observable environment. Dota 2, OpenAI 5 trained on self-play to beat professional human teams. Minecraft and Roblox, being used for open-world exploration and creativity-focused learning. Now, move on to core concepts in reinforcement learning. Firstly, agent. The agent is the learner or decision-maker. It's the AI that takes actions in an environment to maximize cumulative rewards. Examples: a robot navigating a maze, an AI playing chess, a self-driving car avoiding obstacles. Secondly, environment. The environment is the external system with which the agent interacts. It responds to the agent's actions and provides new states and rewards. Thirdly, state S. A state is a snapshot or description of the environment at a specific point in time. In a game of chess, a state is the arrangement of the pieces. Fourthly, action A. An action is a choice the agent makes at a given state. Fifthly, reward R. A reward is the feedback signal from the environment after the agent takes an action. Positive reward, good action; negative reward, penalty. Pass, bad action. Sixthly, policy P. A policy is the strategy used by the agent to decide which action to take based on the current state. It can be deterministic, always the same action for a state, or stochastic, probabilistic decisions. Seventhly, value function, RV. The value function estimates how good it is to be in a certain state, in terms of expected future rewards. And mass expected return, sum of future rewards, starting from state S and following the policy P. Eighthly, Q function, action value function. The Q value function estimates the value of taking a specific action in a given state. T S A, cheese expected return from taking action A in state S and following the policy afterward. Ninth one, exploration versus exploitation. Exploration, trying new actions to discover their effects. Exploitation, using known actions that already yield high rewards. 10th one, episode. An episode is a complete sequence of interactions between the agent and environment, from an initial state to a terminal state. For example, one full game of Pong. Discount factor, Grumain. The discount factor, A0-G, A0G1, determines how much future rewards are worth compared to immediate rewards. Let's go ahead with popular algorithms in game-based RL. Q learning, ideal for simple environments. Deep Q networks, DQN, combines Q learning with deep neural networks. Policy gradient methods focus on optimizing the policy directly. Actor-critic models use two networks, one to act, one to evaluate. Famous milestones they have: IBM Deep Blue defeated chess champion Garry Kasparov in 1997. AlphaGo by DeepMind beat the world's top Go player in 2016 using RL and deep learning. OpenAI 5 played and won against top Dota 2 teams. AlphaStar mastered StarCraft II, one of the most complex strategy games. Next topic is RL in modern games and simulators. So begin with, why use modern games and simulators? Modern games and simulators offer high-fidelity, realistic environments, graphics, physics, sound, multi-agent dynamics, enabling AI versus AI or AI versus human interactions, long-term strategic planning, decision-making, and teamwork. partially observable environments, which reflect real-world uncertainty. After that, AlphaGo and AlphaZero, mastering board games developed by DeepMind. Games, Go, Chess, Show. Next one, DeepMind and Atari 2600. Games environment, Arcade Learning Environment, ALE. Algorithm, DeepQ Network, DQN. Following that, OpenAI Five, Dota 2 developed by OpenAI. Game, Dota 2. A complex real-time multiplayer battle arena game. Another one, AlphaStar, StarCraft II developed by DeepMind. Game, StarCraft II, a real-time strategy game involving base building, resource management, and combat. Next, simulators for robotics and real-world training examples. Mujoko, PyBullet, Isaac Gym, Kala, autonomous driving, Habitat AI, indoor navigation, Minecraft, Roblox, and Unity ML agents. Further, multi-agent reinforcement learning, MARL, modern games often require multiple agents to cooperate, for example, passing a ball in Rocket League. Last one, generalization and transfer. Learning training in games allows agents to transfer skills from one game or level to another. Develop general intelligence, solving a wide range of tasks using shared principles. Here are the challenges and limitations. Sample inefficiency. Requires lots of training data and time. Sparse rewards. Some games don't give frequent feedback. Safety concerns. In real-world applications, exploration can be risky. Overfitting. AI may become too good at one game and fail in others. So now move on to future of RL in gaming and beyond. First comes next-gen game AI smarter, more adaptive opponents. What's coming? Game AI that learns on the fly from your behavior. Enemies and NPCs that evolve over time, creating personalized difficulty. In second row, it comes procedural content generation with RL. What it means. Using RL to automatically create engaging content, maps, challenges, puzzles, tailored to each user. The subsequent one, RL for personalized gaming experiences. AI agents could act as adaptive game companions or dynamic guides, adjusting tutorials based on your learning speed, assistance depending on performance. Afterwards, training grounds for real-world AI games provide low-risk, high-feedback environments ideal for prototyping real-world AI. What's next? Simulated drone racing, real drone delivery optimization. RTS games, arms logistics, defense, or disaster response AI. After that, RL-driven non-player characters, NPCs. Current NPCs follow scripted routines. Future with RL, NPCs that learn social behaviors and goals, agents that form alliances or rivalries over time. Following that, metaverse and VR/AR applications. In the metaverse, where persistent and interactive virtual spaces are key, RL will train virtual assistants that learn your habits, control avatars and bots in realistic simulations. The next one, ethical RL, fairness, bias, and controllers. RL systems become autonomous and adaptive. They also raise ethical questions. Will game AIs manipulate users for engagement? How do we prevent toxic or exploitative AI behavior? Following one, generalization and lifelong learning. Current RL agents often forget old tasks when learning new ones. In the future, agents will be able to retain past knowledge while learning new games or skills. Lastly, beyond gaming where real-world applications of RL takes place. Now move on to the conclusion part. Reinforcement learning has transformed how we think about AI and its potential. From mastering classic board games to complex video games, it has proven that machines can learn, adapt, and even outplay human intuition. As we look ahead, the lessons learned from games will influence robotics, education, autonomous systems, and much more. The world of reinforcement learning is just getting started, and the game is far from over. Thanks for watching Reinforcement Learning: How AI Masters the Art of Playing Games. If you enjoyed this video, don't forget to like, subscribe, and share. Until next time, keep learning, keep playing, and stay curious on AI and technology.